Okay, let's move on now. So let's look at um, specific form of um, Gaussian processes. So for example, there is something known as Gaussian Sinc process. Okay, so what is a sinc function? Can somebody tell me what is a sinc? If I say sinc of x, so how do you define sinc? It is sin x over x, right? So if you plot it, how does it look like?
Decaying
So
sign.
yeah, so it's at 0 it is 1, right? The height would be 1, and now it will be sine on, and then it decreases with x. At, for example, at certain x it will be 0, right? What will be the x at which it will be 0? Whenever sine x is 0, it will be 0. So it will cross over at something like this, and similarly, I don't know, I'm really bad at writing these things, but yeah, it's symmetric around x, around y axis, and this crossover point would be pi. This would be 2 pi, 3 pi, and so on, right? This is what you get. You agree? Hmm? Now, if I take, for example, sine x, sorry, sinc x, this is what it is. If I take another function which is like this, what can I say about this? So at pi it will be 1. Essentially, it's a shifted version of whatever. It's symmetric around this. So what can you say about this function? The earlier one is sinc x. What is this? Is it sinc x? Hey, signal processing guys, you should be able to say
X plus x minus pi.
x minus sinc of x minus pi. Is that correct? Ayush?
Yes, sir, correct. X
Yes,
sync of X
right?
minus pi.
Yeah. Sumit, are you there? Okay. So this is sinc x minus pi. Now, if you multiply sinc x and sinc x minus pi, integrate, what do you get? If I integrate these two, what do you get? Any idea? I'll integrate from minus infinity to infinity. What do you get? Okay, I'll modify this a little bit. Okay, so um, um, okay, so just do this modification just to follow the notation in the book. So now this is the modification for the sinc function. So sinc x, now onwards I'll define it as sine of pi x divided by pi x. Okay, this is how I'm going to define. So now instead of what are the crossover points? X equal to 0, you'll get 1. X equal to 1, you'll get 0. X equal to 2, you'll get 0, and so on. Instead of pi, 2 pi, 3 pi, you'll have 1, 2, 3, etc. That's the only difference. Okay. Now what should be the delay? The delay should be, so instead of earlier you had sinc of x minus pi, now you should have sinc of x minus 1, x minus 2, x minus 3, and so on, because you have pi into x minus 1, which is pi x minus pi, right? Is that okay? Now what can you say about minus infinity to infinity sinc of x minus n and sinc of x minus m dx? What can you say about this? Can you intuitively see what's happening here? Yes, Jayant?
Sir, will it be 1, sir?
Huh? 1 always? Ayush?
Yes, sir.
M has to be equal to 1. For M is equal to N1, then it will be 1.
Huh? Yes. So n and m are equal, then it will be 1, right? So it will be Kronecker delta. Delta in m. So it's 1 whenever n equal to m, 0 otherwise. You have seen this, right? Ayush?
No, sir, not seen.
No?
But
Hey, in your signal processing, you should have seen this.
I know.
Yeah. So not just
ISI,
interpolation.
I
Hmm?
ISI,
sampling,
in,
reconstruction.
intersimple interference, sir. To
No,
get
you
the
should have seen
condition.
this as when you studied sampling theorem, right?
Yes,
Yes,
sir.
sir.
No? Ayush?
Yes, sir.
Yes, sir. Yes. So like rectangular window goes to sink in Fourier domain, something like that.
Yes, sort of. But okay, so we will see that soon. So this is fine, right? This particular thing. So what does this indicate? This indicates that sinc x in this definition, sin pi x over pi x, forms a orthonormal functions, right? Because they are orthogonal. That means when you multiply them and integrate, you'll get 0 whenever n is not equal to n, 1 otherwise. So it's an orthonormal functions, right? So now I can do exactly same as before, right? So I can do x of t equal to, so I'll generate a bunch of IID or independent Gaussian random variables, do a linear combination using sinc. Okay. So before that, let's look at an important thing. So for example, let's say I have a signal which is x of t is, let's say, band limited. So what do you mean by that? If you look at the Fourier transform of this, right, is equal to 0 for all f greater than or equal to or greater than b. Okay. That means the Fourier transform of x of t will be 0 for outside the bandwidth b. Okay. So this is called a band limited signal. I hope all of you are familiar with this, right?
Yes.
Okay. So now, if you have a band limited signal, I can write x of t as a linear combination of sinc, right? So
Sir,
how do
B
you do that?
real
Huh?
number, sir. B
Huh?
could be any real number.
Sorry?
Sir, B, this capital B.
This is a real number, right? This is a number, positive number. Okay. So now x of t can be written as summation over all n. Interestingly, this can be written as x of n by 2b sinc of 2bt minus n. Okay. So what is this? So for example, if you have a signal like this, suppose you have a signal like this and you sample, suppose assuming that this is band limited, meaning the Fourier transform is 0 beyond capital B, then if you sample at, let's say, 0, and then you sample at 1 by 2b, right? So what is 1 by 2b? So somewhere here, this is 1 by 2b, then 2 by 2b, and so on. If you take all these samples, right, these corresponds to the coefficient x of n by 2b here. And if you want to reconstruct x of t from this, all that I have to do is I have to multiply it by sinc and sum. This is called sinc interpolation, right? So if you have these samples here like this, I'll just multiply this by a sinc like this, and then multiply this by another sinc and add them, right? When you add them, I'll get x of t, right? This is your sampling theorem, right?
Sir, uh,
Yes.
so can we visualize it like in Fourier domain, if we have band limited, like for example, rectangular kind of a filter or window, if we go in time domain, it will be sync. So
Yes.
that is what sync here the equation so is.
No, what you are looking at is a very special case, right? So if you have, for example, band limited, right? So let's say you are saying this is what you have, right? So minus b and b, right? So this is in the Fourier domain, right? So what will be the corresponding signal in time domain? X of t. What will be x of t? Yeah, sinc, right? Right. So now if I want to know, so how do I write x of t? I can write this using these samples, right? I'll take these samples sufficiently far. The width would be 1 by 2 times the bandwidth, right? So I can take this, and using these samples I can reconstruct. So how do I reconstruct? I put sinc at each place and add them. Interestingly, in this case I get another sinc. Okay.
Yeah, yes.
Is this fine? So I can try it out. I can again write a program for this. See what will be the coefficients. Okay. So what is the relationship between, for example, this and this x of t and x of n by 2b? Okay. So let me rewrite the old function x of t. Your orthonormal thing would be minus infinity to infinity some ak pk of t. So how do I get, assume that this is orthonormal. So how do you get ak? So you just multiply it by, let's say I want to get am, so multiply it by phi m of t, integrate, right? So what do you get? You get summation k equal to minus infinity to infinity, okay, ak, assuming that you can interchange the integral and this infinite sum. So this is what you get, right? Phi m of t dt. Okay, this is where you need monotone convergence and all that. I mean, dominated convergence and all that. Okay, so this is again overall k, ak. So what will happen to this vk pm? This will be delta km. So this is whenever k equal to m, this will be 1, otherwise 0. So they will get am. So the coefficients can be obtained by multiplying by the corresponding basis and integrating, right? So similarly, I can get x. So this coefficient, right? So x of n by 2b. So I can get x of n or m by 2b. I can get this by multiplying x of t by sinc, right? What should I multiply this with? 2bt minus not n m dt. So what do you think this whole operation is? Huh? Take, see, this is interesting, right? So this whole inner product is essentially you are taking, suppose if this is the signal, you are taking the mth sample, that's all, right? This is the 0th, this is the first, second, third, and so on. You look at the mth one. So this is the mth sample. The corresponding amplitude is given by this inner product. Okay, so although in integral form this is complicated, in terms of implementation it's very easy. You just have to sample at that particular time instant. On the other hand, in a general case where supposing you don't use sinc, then finding the coefficient amounts to evaluating this integral. In this case, this integral evaluates to the sample at time instant m. Okay. Now there is something known as sinc Gaussian process, okay, or Gaussian sinc process. So what do? So you take xn, okay, so you take for example an IID sequence of xn, 0 mean variance sigma squared, and then do this n equal to, you just sum it over from minus infinity to infinity, xn sinc of 2bt minus n. So the corresponding process x of t is called a Gaussian sinc process. All that I'm doing is amplitude is chosen according to Gaussian IID, and I'm going to put a sinc at each of these positions and then add all of that. That resulting function is x of t. Okay, is that fine? Now the next question is, well, we have constructed such a process. How do you find, for example, the mean and covariance, right? The mean is 0 in this case. The covariance function is something that we need to compute, which will turn out to be easy thing to compute here. Okay, it's easy to compute the covariance. So yeah, this is all about the Gaussian process. Now the question is, what happens to this when you pass it through some systems and so on? Okay, any questions? Any questions? Hmm? Okay, one thing that I didn't mention is, you know, if the process is Gaussian, sorry, if the Gaussian process is stationary, I can write it as a linear combination of these orthonormal functions. Okay, for example, sinc functions. So if you look at any stationary Gaussian process, I can always write it as linear combination of orthonormal, and therefore I can study what happens when you pass that through a linear time invariant filters and so on. Okay, so that's why we look at such representation. Otherwise, it's very complicated. You don't know how to analyze what happens when you send this process through a filter or some system. Okay, any questions? Yes, Ayush. Yes, go ahead.
Sir, here the whatever the we are taking the integral, sir.
Huh?
It's an integration we are taking, na, sir.
Yes,
So it is, sir, basically, sir, we are defining the inner product using that integral,
correct.
and then we are talking about this orthonormality and everything, no, sir.
No, you start with the orthonormal functions and then construct a Gaussian process out of it. It's not the
Yes, sir.
other way.
Once, no, sir. Initially,
Hmm?
we are taking the orthonormal function. So
Mm-hmm.
to take that one, we have to have a inner product space, no, sir, first. Otherwise, how can we talk about the orthonormality, sir?
Okay. So for you, I didn't go over that. So what I'm looking at is, for example, this, this set of function space, which is all those functions such that the integral of this is less than infinity. This is square integrable functions. And on this, I'll define f comma g. Okay.
So
And
we are
this
taking this
integral,
space.
uh,
This L square space we are talking about, no, sir.
yeah, this is basically L2.
Yes.
Is that fine?
Yes, sir.
I mean, if you want to be very rigorous, then you to look at the L2 space and then define an inner product on that. That will result in what is known as a Hilbert space. And then we are looking at that Hilbert space. Especially the moment you have a Hilbert space, I can define orthonormal functions. Then I'm going to construct a random process using that by sampling from Gaussian, basically generating Gaussian random variables and then multiplying it with the corresponding orthonormal functions and adding them to get a Gaussian process. Is that fine?
Yes, sir. Yes, sir.
Yeah. Any other questions? So Ayush,
So actually, sir, the existence of these orthonormal functions are coming from that inner product only, no, sir.
yes. That's what I wrote, right? The integral of sinc of t minus m times sinc of t minus n, right? So those are orthonormal. That's the inner product. Yeah. Ayush, yeah, sorry. Questions,
No,
Ayush?
not.
No questions. Praveen?
No.
No questions. Okay. Jayant?
Sorry, about last class, I have a doubt.
Yes.
Sir,
Last?
while last class,
Okay.
sir, while deriving conditional uh, probability density, sir, for
Uh-huh.
jointly Gaussian random vectors,
Correct.
you have done completing square methods for
Correct.
matrices,
Correct.
but I did not understand how will we, in that same page from first line to second line?
This one, right?
Yes, sir. How?
Hmm?
Yes, sir.
Okay, so one
We
way is
can
you
go from
multiply.
the second line to first line, sir. From
Yeah.
first line to second.
Okay, so essentially, what is the form that you need? You need this form, right? X plus mu transpose K inverse X plus mu, right? That should be equal to this thing. Now figure out what should be mu and what should be K. That's all.
Yes, sir.
Yeah, do algebra. I'll leave it for you.
Okay, sir.
See, you can see, right? So what is this? This is X transpose K inverse X. That is one term. So K inverse should be B, done. Or B should be K inverse. So that's why you have B here, right? See, one term you are already done. What about the other term? So X transpose K inverse mu, right? That's another term, right? And you have mu transpose K inverse X. I can again do the transpose and write this as 2 times X transpose K inverse mu, right? See which one corresponds to that and so on.
Yes, sir. Okay, sir.
Yeah. Okay. Any other questions? Okay, Shruti and anyway, Savan is the TA. So, Shruti,
Hello, sir. Yeah.
you have any questions?
No, sir.
Okay. Okay. So I think homework is online. Just solve those problems and submit it on what is the deadline in Savan? 10th? No, sorry.
10th.
10th. Okay.
Yeah, I changed it to 10th.
Okay, fine. Okay. Yeah. If there are no questions, then we'll stop here.
Thank you, sir.
Okay. Yeah. Thank you.